Okay, let's unpack this. Almost a century ago, Edwin Hubble made a truly foundational discovery.
Mm,
The universe isn't static, it's expanding.
yeah, quite the revelation.
And get this, his initial evidence, it relied on observing these fascinating blinking stars called Cepheids.
Mm-hmm.
Fast forward to today, and that nearly century-old work is still incredibly relevant.
It really is. What's fascinating here is how a seemingly simple idea, uh, you know, galaxies receding faster the farther away they are, has blossomed into one of the most, well, actively debated topics in modern cosmology.
Exactly. So for this deep dive, we're heading straight into the Hubble constant, often written as H0. Now, on the surface, it looks pretty straightforward, right?
You'd think so.
There's Hubble's law. Velocity equals h0 times distance.
Mm.
V equals h0d. Simple enough.
But as we'll definitely see, pinning down that single number, H0, has become anything but simple. Our exploration today takes us through some really insightful material, really delving into the history, the methods, and, well, the ongoing challenges.
And our mission, which you've already signed up for just by tuning in, is to understand why figuring out the precise value of the Hubble constant is such a cosmic puzzle.
Right.
And maybe more importantly, what are the implications of this uncertainty? We're aiming for those aha moments, giving you the quick but thorough knowledge you're after.
Okay, let's start right at the beginning then, with Hubble himself. His work, early 20th century, established this relationship between a galaxy's distance and how fast it's moving away from us, its recession speed.
And he figured out these distances using Cepheid variable stars. I like to think of them as cosmic lighthouses, sort of with a predictable flicker.
That's a good analogy, because their brightness changes in a really regular way, and there's this known link between that rate of change,
Yeah.
that period, and their actual intrinsic brightness.
So astronomers could use them as standard candles.
Yeah.
Helps estimate how far away these galaxies were.
Exactly. It's also important to remember, though, that Hubble's observations weren't happening in a vacuum, so to speak.
Right, there was theoretical work happening too.
Right. Yes, they followed some pretty profound theoretical work by Alexander Friedman and Georges Lemaitre, working independently, mind you.
And this was based on Einstein's general relativity.
Correct. They predicted, basically, that the universe could indeed be expanding.
So Hubble provided the observational muscle, the proof, to back up the theory.
Pretty much, yeah.
Now here's where it gets really interesting. Hubble's first estimate for this constant, H0, well, let's just say it was significantly higher than what we measure today.
Oh, definitely. He landed somewhere around 500 kilometers per second per megaparsec.
500, wow.
Indeed. That's dramatically different from the values we talk about today. It really highlights how much our understanding and, our measurement techniques have improved over the last 100 years or so.
And that unit, kilometers per second per megaparsec. Maybe we should break that down quickly.
Good idea. It sounds like a mouthful. But essentially, it just tells us how much faster a galaxy seems to be moving away from us for every extra megaparsec of distance.
And a
Now,
megaparsec is huge, right?
immense. A parsec is about 3.26 light years, so a megaparsec is a million of those. Truly cosmic scales.
Okay, so we've got Hubble's initial work. But the term Hubble constant itself needs a little clarification, doesn't it? It's not constant, like the speed of light is constant.
That's a crucial point, yeah. In our standard cosmological models, the actual rate of expansion changes over cosmic time.
Ah.
So when we talk about the Hubble constant, H0, we're specifically referring to the present-day value of what's really the Hubble parameter. That parameter describes how the universe's expansion rate evolves.
And this evolution, this speeding up or slowing down,
Yeah.
that's linked to something called the deceleration parameter, Q. I remember reading about that.
Exactly. The deceleration parameter Q, it's basically a way to measure how the expansion rate itself is changing. Is it speeding up or slowing down?
And for a long time, people thought it was slowing down.
That was the prevailing idea, yes. That Q was positive, meaning the expansion was slowing down thanks to the gravitational pull of all the matter in the universe.
Which makes intuitive sense. Gravity pulls things together.
Right. And a positive Q also implied that the age of the universe was actually less than the inverse of the Hubble parameter, 1 over h, which is roughly 14 billion years.
So a positive Q meant a younger universe than that simple calculation might suggest.
Precisely. For instance, a value of Q equals 0.5, which was quite popular among theorists for a while, that would have put the age of the universe at about 2/3 of 1 over h. So significantly younger.
But then came a major plot twist in the 1990s, right?
Oh, yeah. A huge discovery. the accelerating universe.
Tell us about that. That really changed everything.
It was completely revolutionary. Observations of distant supernovae, these type Ia supernovae, revealed they were fainter and therefore farther away than they should have been if the expansion was slowing down.
So they were further than expected.
Exactly. This unexpected finding indicated the universe wasn't just expanding, it was actually speeding up, accelerating its expansion.
Which then led to the whole idea of dark energy, this mysterious force pushing everything apart.
Correct. The realization that the deceleration parameter, Q, is apparently negative. Well, it has profound implications. It actually means the universe could technically be older than 1 over h, though current estimates still place its age very close to that value, interestingly enough.
Wow. And just to make things even more complicated, individual galaxies have their own motions too, right? These peculiar velocities.
Yes, that's another layer. These velocities are independent of the overall cosmic expansion. They're caused by, local gravitational interactions between galaxies, clusters pulling on each other.
So you have to account for those local movements when you're trying to measure the big overall expansion.
Absolutely. They need to be carefully subtracted or accounted for, especially when using relatively nearby galaxies to gauge the Hubble flow. These local motions definitely complicate things.
Okay, so figuring out 8-0 is clearly not as simple as Hubble's first equation suggested.
Not at all.
Now let's talk about how we actually try to measure this thing today. The material we looked at talks about late universe methods. What are those about?
Right. Late universe methods are essentially about building what we call a cosmic distance ladder. It's a step-by-step process.
Okay, like climbing a ladder to see further.
Kind of, yeah. We start with relatively nearby objects where we can measure distances directly, or at least with very high precision. Things in our own galaxy, maybe nearby galaxies.
Like using parallax with Gaia.
Exactly. Parallax is a key first rung. Then we use these well-measured nearby distances to calibrate the brightness of certain standard candles or properties of standard rulers found in those objects.
Like the Cepheids we mentioned earlier.
Precisely. Cepheids are a crucial rung. Then we find those same standard candles in more distant galaxies, measure how bright they appear, and since we know how bright they really are from the calibration step, we can figure out their distance. You keep doing this step by step, further and further out.
Until you reach galaxies far enough away that their motion is dominated by the overall Hubble expansion, not just those peculiar velocities we talked about.
That's the goal. And the research we've been reviewing suggests that data from Cepheids and other astrophysical standards, well, they've largely converged on a late universe value of around 70 kilometers per second per megaparsec, give or take.
Around 70?
Okay.
And there are other runs on this ladder besides Cepheids.
Oh, yes. Another important one mentioned uses the tip of the red giant branch, or TRGB.
Tip of the red giant branch. What's the idea there?
The physics is pretty neat. It turns out that red giant stars, as they evolve, reach a very specific, predictable peak brightness just before they ignite helium fusion in their cores, the so-called helium flash.
Ah, so they all hit roughly the same maximum brightness at that point.
Essentially, yes. For stars below a certain mass, anyway, this consistent peak brightness means we can use them as another type of standard candle to estimate distances, especially to nearby galaxies where we can resolve individual stars.
And what are the latest results using that method? Are they close to the Cepheid ones?
Pretty close, yeah. The material mentions recent estimates from the Hubble Space Telescope using this TRGB method, giving a value of about 69.8 plus or minus maybe 1.9, so very near 70.
Okay.
And interestingly, when they combine that with really precise distance measurements to a globular cluster called Omega Centauri, using data from the Gaia mission.
Gaia again. It
Yeah.
pops up everywhere.
It's revolutionary for stellar astrophysics. Anyway, combining HST TRGB with Gaia data on Omega Centauri yields a slightly higher value, 72.1 plus or minus 2.0, still in that low 70s ballpark.
Okay, so these late universe methods seem to be clustering around the low 70s. Now let's circle back specifically to Hubble's original tool, the Cepheid variables. They're still super important today, right?
Right.
Especially because of Gaia.
Absolutely crucial. Henrietta Leavitt's discovery way back in 1908, finding that relationship between a Cepheid's luminosity and its pulsation period, that was the key that unlocked extragalactic distances.
Because if you measure how fast it blinks,
You know how bright it truly is? Its intrinsic luminosity. Then you compare that to how bright it looks in the sky, its apparent brightness.
and boom, you can calculate the distance.
Exactly. It's a beautifully elegant method.
And Gaia has just supercharged this by giving us these incredibly precise parallax measurements for Cepheids right here in our own Milky Way.
Totally. Parallax, measuring that tiny apparent shift in a star's position as Earth orbits the sun, gives us a direct geometric distance measurement. It's the gold standard for the first rung of the distance ladder.
And the source material gave an example, RS pup.
Yeah, RS-pup, a long-period Cepheid. The Gaia DR2 data provided a parallax for it that translates to a distance of about 1710 parsecs, plus or minus only 80 parsecs. That's pretty good precision for something that far away.
And Gaia found loads of these things, didn't it?
Thousands. Gaia DR2 cataloged over 9,500 stars classified as Cepheids, a massive data set for calibration.
Okay, so how have these much better Cepheid distances affected the actual Hubble constant measurements? Because some teams have really focused on this path.
Right. For years, some of the strongest evidence for a higher value of H0, maybe closer to 73 or 74, has come from specifically using these Gaia-calibrated Cepheids to then calibrate the distances to galaxies that have also hosted Type Ia supernovae.
Ah, the supernovae. Those are the standard bombs, right? Even brighter than Cepheids.
Much brighter, yes. Type Ia supernovae are incredibly luminous explosions, and they have a very consistent peak brightness after certain corrections. This makes them fantastic standard candles for measuring distances much, much further out into the universe.
But you still need to know the exact brightness of that peak, which means you need to calibrate them using something closer where you also see Cepheids.
Precisely. You find galaxies that have both Cepheids and have hosted a Type Ia supernova. You use the Cepheids to get an accurate distance to the galaxy, which then tells you the true peak brightness of the supernova in that galaxy. Then you can use that calibrated supernova brightness to measure distances to even more remote galaxies that only have supernovae visible. It's that ladder again.
And the research team, led by Adam Rees, they've been major players in this, consistently getting these higher values for H0.
That's correct. Our sources detail a whole series of their studies showing a progression. Back in 2016, using Hubble Space Telescope observations of Cepheids and refining the distance to one of our satellite galaxies, the Large Magellanic Cloud, they got a value of around 73.2, plus or minus about 1.7.
Okay, so already in the 73 range back then.
Yes, and they've kept refining it. They incorporated more HST parallax measurements of Milky Way Cepheids, and then, crucially, the improved Gaia parallaxes as they became available, like from Gaia DR2 and then the even better EDR3.
So the better the Gaia data got, the more precise their H0 became.
It seems so. In their 2021 paper, using 75 Milky Way Cepheids with HST photometry and these Gaia EDR3 parallaxes, which are really good, they arrived at a value of 73.0 plus or minus 1.4.
Getting tighter error bars.
Definitely. And when they combine this Milky Way calibration with other independent Cepheid calibration anchors, like the Large Magellanic Cloud work, they reach their current best estimate of H0 is 73.2 plus or minus 1.3 kilometers per second per megaparsec.
Wow, that's down to 1.8% precision. That's incredibly precise for measuring the expansion of the entire universe.
It's a remarkable achievement in observational cosmology, no doubt about it.
And it's a big but, even with this incredible precision, we still have this fundamental disagreement with other methods, right? The source mentioned a specific issue here.
Indeed. This highly precise late universe measurement, primarily from recent collaborators using Cepheids and supernovae, has this persistent, notable discrepancy with the values obtained from what we call early universe methods.
And the difference isn't trivial.
Not statistically speaking, the difference is about 4.2 sigma compared to the results from the Planck mission, which studied the early universe.
4.2 sigma. Okay,
Yeah.
for listeners, what does that mean in practical terms?
Well, in statistics, finding a difference at the level of 4 sigma, or even higher in some analyses, means there's a very low probability, like less than 1 in 10,000, that this discrepancy is just a fluke, just random statistical error.
So it strongly suggests there's a real underlying issue, either with the measurements or with our understanding of the universe itself.
That's the crux of the problem, yeah. It's not something that seems likely to just go away with slightly better data.
Okay, let's switch gears then and talk about these early universe methods. You mentioned Planck. These are based on the cosmic microwave background, the CMB.
That's correct. The CMB is essentially the afterglow of the Big Bang. It's the oldest light in the universe, released when the universe was only about 380,000 years old.
Just a baby, cosmically speaking.
Exactly. And this light isn't perfectly uniform. It contains tiny temperature fluctuations, like ripples on a pond.
And these ripples hold clues.
A wealth of information. By studying the patterns, the sizes, the distribution of these tiny temperature fluctuations in the CMB across the entire sky, we can infer a huge amount about the conditions in the early universe and the fundamental parameters of cosmology, including the Hubble constant.
So wait, how does light from 380,000 years after the Big Bang tell us how fast the universe is expanding today, nearly 14 billion years later? What's the connection?
It's quite intricate, but the key is that the patterns we see in the CMB, especially the characteristic size of the hot and cold spots, are related to sound waves that were propagating through the primordial plasma before the CMB was released.
Sound waves in the early universe.
Yep, acoustic oscillations. The size of the patterns we observe today depends on how far those sound waves could travel before the universe cooled enough for neutral atoms to form and the photons of the CMB to stream freely. This sets a standard ruler in the early universe.
Okay, a standard ruler imprinted on the CMB.
Exactly. By measuring the apparent angular size of this ruler on the sky today and knowing its actual physical size from the physics of the early universe, we can determine the geometry of the universe and its expansion history between then and now.
And that allows you to calculate what H0 must be today, assuming our standard model of cosmology, lambda CDM, is correct.
Precisely. It's an inference based on fitting a model to the early universe data and extrapolating forward.
And the Planck mission, which followed up on an earlier mission called WMAP, gave us our best look yet at this CMB.
By far. Planck provided incredibly detailed maps of the CMB with unprecedented precision.
So what's the verdict from Planck? What's their estimate for H0?
The latest Planck estimate, based on their full analysis of the CMB data within that standard lambda CDM model, is H0 equals 67.66 plus or minus only 0.42 kilometers per second per megaparsec.
67.66. Plus or minus less than half a unit. That's also incredibly precise.
Extremely precise, yes.
Yep.
Some percent precision.
Okay, so now we have two very precise measurements using completely different approaches looking at totally different eras of the universe. One cluster around 73.
From the late universe distance ladder, Cepheids, supernovae, TRGB.
And the other is firmly at 67 point something.
From the early universe CMB data interpreted through our standard cosmological model.
And that difference between roughly 73 and roughly 67.6, that's the Hubble tension everyone talks about.
That is exactly it. While the numerical difference, about 5 or 6 units, might sound small in everyday terms, the precision of both measurements makes it a really significant disagreement.
It's not just overlapping error bars.
No, the error bars are small enough now that they don't really overlap significantly. It's like, as the source material hinted, two teams measuring the same table with incredibly accurate laser rulers and still getting consistently different lengths.
Which makes you question either the rulers or maybe the table isn't as simple as you thought.
That's the perfect analogy. Is there some unknown error, a systematic effect, hiding in one or both types of measurements? Or is our understanding of the table, our standard model of cosmology, incomplete?
And this Hubble tension, it's a really big deal in cosmology right now, isn't it? It's not just some minor squabble over the third decimal place.
Oh, it's huge. For decades, cosmologists felt like things were converging nicely, especially with the standard lambda CDM model seeming to explain so much. From the CMB to large-scale structure, we thought we were homing in on H0.
And the late universe measurements seem to be settling around the low 70s.
Exactly. But then the incredibly precise early universe data from Planck came along and basically threw a major wrench in the works, giving this significantly lower value.
And the tension has only gotten worse as both sides have improved their precision.
Pretty much, yes. The error bars have shrunk, but the central values haven't really moved enough to reconcile.
So what could it mean? If it's not just measurement error, what are the implications?
Well, this is where it gets really exciting, potentially. This discrepancy could be our first solid observational hint of new and exotic physics, something beyond our current standard cosmological model.
New physics. Like what?
It could mean there's something we don't fully understand about, say, stellar evolution, particularly the behavior of Cepheids or type Ia supernovae, which would affect our distance measurements in the late universe. Or it could point to new physics operating in the very early universe, perhaps involving different forms of dark energy or dark matter or modifications to gravity that would change the expansion history inferred from the CMB.
So it could challenge our understanding of stars or challenge our understanding of the very beginning of the universe itself.
Wow.
Either way, it's potentially revolutionary.
Now, our source material mentioned a couple of potential ways people are trying to resolve this tension, maybe without invoking brand new physics entirely. One was the idea of a local bubble. Right, the local void, or Hubble bubble idea. The hypothesis here is that perhaps we, the Milky Way and our nearby galactic neighborhood, happen to reside in a region of the universe that's slightly less dense, slightly emptier than the cosmic average.
Like we're in a bit of a cosmic underpass.
Sort of. If that were true, the local gravitational pull would be weaker, allowing our local patch of the universe to expand slightly faster than the global average rate that's inferred from the CMB, which represents that average.
So our local measurement of H0 using the distance ladder would naturally be a bit higher than the global H0 from the early universe.
That's the idea. It's plausible, but most studies suggest that the size and emptiness needed for such a bubble to explain the entire tension would have to be pretty significant, maybe larger than observations currently support. But it's still being investigated.
Okay, interesting. And the other possibility mentioned was weak gravitational lensing affecting the supernova measurements. How does that work?
Yeah, weak lensing. As light from those very distant type Ia supernovae travels billions of light years towards us, its path gets slightly bent by the gravity of all the intervening matter galaxies, dark matter halos, etc.
Like little cosmic lenses distorting the view.
Exactly. These subtle distortions can slightly magnify or demagnify the apparent brightness of the supernovae. If we don't account for this lensing effect perfectly, it could introduce a systematic bias in our distance estimates based on supernovae brightness.
Now, that bias could maybe push the calculated H0 value up or down.
Potentially, yes. People are working hard to model and correct for weak lensing effects, but it's complex. It's possible that residual uncorrected lensing effects could be contributing somewhat to the tension, although again, most analyses suggest it's probably not enough to explain the whole difference on its own.
So no easy answers yet. It really seems like this seemingly simple number, the Hubble constant, well, it's turned into this massive puzzle
It really has.
with potentially revolutionary implications for how we understand the entire cosmos. It's almost humbling, isn't it? Thinking about trying to measure the expansion of something so unimaginably vast based on, the faint flickering light from stars billions of light years away.
It absolutely is. We've journeyed from Hubble's initial groundbreaking discovery, using those Cepheids, spotting that first hint of expansion,
Right, with his estimate of 500.
all the way to this modern-day conundrum where incredibly precise measurements, using vastly different techniques, looking at opposite ends of cosmic history, are giving us significantly different answers. It's a fascinating time in cosmology.
Okay, so as we wrap up this deep dive, I think the key takeaway is pretty clear. This number, H0, the Hubble constant, which seems like it should be straightforward, well, it's actually right at the heart of a major active debate in cosmology.
Definitely.
We have different, highly sophisticated methods giving us conflicting results. And this Hubble tension, it really could be pointing towards fundamental gaps in our understanding. Maybe new physics is just around the corner.
It might well be ushering in an era of new and exotic physics, just as the sources suggest, or perhaps a deeper understanding of the complexities within our current framework.
So this really raises an important question for you, the listener, to ponder. Which measurement do you think will ultimately win out? The late universe local measurement or the early universe global one derived from the CMB?
Or maybe, just maybe, the discrepancy itself is the most important clue. Perhaps the tension holds the key to unlocking a deeper, more nuanced understanding of this vast, incredible, and ever-expanding universe we live in.
It really makes you consider the sheer scale we're dealing with and the incredible challenges involved in trying to measure these fundamental properties of reality.
Absolutely. It's a powerful reminder that our cosmic story is still very much being written, and you've just taken a deep dive into one of its most fascinating and currently wide open chapters.